There. Okay.
Yeah. All right. Okay. Gotcha. Yeah, can you see my screen? Nampak? Screen saya nampak kan?
Nampak?
Okay. Okay. Assalamualaikum warahmatullahi wabarakatuh. I hope everybody is doing well, right? So last week you have a 1 week semester break, isn't it? So I hope everybody have a good time with the family. Okay? And now we're going to continue with week 7, isn't it? So we are in week 7, and we have another 2 weeks before we take another break for the Christmas as well as the New Year. Isn't it? So you have another 1 week, and then we continue for the rest of the semester. Okay. Before we proceed, next week will be our test one on Wednesday. Can we do that?
Rasanya boleh je saya.
Boleh sir.
Yeah. So kita buat during ni lah, during class lah, class hour. So I'm going to give you the test questions through Google Classroom, and then you complete within 1.5 hours, and then you submit again through Google Classroom. Okay, right. So the topic covers from the very beginning. I mean, we have a topic on the fundamentals of electric drive, electric magnetic circuit, everything. And then you have this DC motor. So we're going to cover up to the last video, the last video on the DC control, the steady state of this converter. Yeah. Uh, so today we're going to continue with the closed loop. The closed loop control of the DC motor will not be covered. Okay, it's just up to the dual converter that we discussed on the last video. Okay, right. So we have already 19 students join in. Okay, so today we're going to continue actually for the closed, we call it as a closed loop system of a DC drive. So this is a complete, the whole complete system, right? So last video actually discussed on the open loop system, whereby if I can go back to the previous slide, okay, so this is what we did on the last video. So we talked about how to control the speed of the motor, and we always show the example, all the examples actually on the separately excited DC motor. For this subject, EPO 6.0, we mainly basically we look into the separately excited DC motor, and I'm not sure whether we have the series examples. So mostly on the separately excited DC motor. So I'm going to review again, look back on the final exam question, the past final exam question. Uh, is there are there any question related to series DC motor? Okay, but most of the examples that I shared with you and the slide that given to me, we have this only separately excited DC motor that we focus on. Okay, so we look into the how we're going to control the speed of the DC separately excited DC motor by means of one is by controlling the resistor rate. We have these three um, quantities that control the speed of the motor, which is resistance, armature resistance control, and then we have two other control, which is the we control the armature voltage or terminal voltage. We change the voltage and the speed also will change. And then we also have this field flux, the flux change, the flux control. So we control the flux, then we are able to control the speed. Okay, so we have three technique here. Yes, okay, and then we look into the how to control the resistance in armature circuit, but this is it's not really frequently used in the control of the DC motor because of some heating problems, some loss, a bit of loss. So mostly we're going to focus on this terminal voltage flux, terminal voltage control, armature voltage control, and field flux control. Okay, so the last video we discussed on the solid state control, isn't it? Whereby if we have the input supply voltage in terms of AC, then we use the rectifier. And if you have the input side, it's a DC supply, then we have this DC uh, a converter to be able to control the speed of the motor. Also, we look into this circuit, two types of circuit, which is control rectifier, and we have a DC-DC converter. And the most important thing is the 4-quadrant operation. You need to understand. I found out there is a lot of YouTube a video that discuss on what's a 4-quadrant operation. So you must really understand what is a 4-quadrant operation, because this is the basic of how the motor can be controlled, depending on the speed against the torque of the motor. Okay? So this is the speed of the motor, and this is the torque that developed by the by the motor. Okay, so we have quadrant 1, quadrant 2, quadrant 3, quadrant 4. So again and again, look again what is this 4-quadrant operation, and therefore you can appreciate and you can understand more on how to control the speed of the DC motor. Okay, then we have this is actually, we call it as a steady state equation. We develop a steady state equation on the relationship between the output, the speed, and the armature voltage. Right? So we develop the speed, the steady state equation. The steady state equation doesn't involve any transient, any step change. Okay, so we just look into the running operation, the steady state operation of a motor, and the relationship between the speed, this is the speed, and armature voltage, or we have a speed against this flux voltage here. Okay, and therefore that will actually be the basis of how we're going to do the closed loop control of the whole system here. Okay, so we develop the steady state equation, and this is the basic equation again. Okay, all the basic equation, steady state operation, and finally we found out that the voltage and the speed can be controlled by using that equation, right? And therefore, if you control the VA here, you can control speed, or you can also control the IF to increase or lower the speed. Right. Next, and then we look into the rectifier and the chopper circuit. So we look into, this is covered by power electronic subject last semester. We have this power electronic subject that discuss on the half wave, full wave, rectifier. Okay, so we go through the single phase, half wave, and this is when we have a discontinuous operation, right? And we have a discontinuous operation of the current. Look at the current. So the current is discontinuous. So when you have that discontinuous current operation, you have a different output voltage. But when we discuss on the continuous current, whereby if you have the current is continuous, I think there's a slide there. Okay. So when we have a continuous armature current, then you are no longer have the same output voltage waveform as the previous waveform there. Okay. So this is for the continuous current operation, and then we have this equation, right? So this is the steady state equation to describe the output voltage, right? And we have this alpha, which is the firing angle, or you can, there are terms. Alpha can be the firing angle, or sometimes known as a delay angle. Okay? There are two terms that refer to alpha, which is firing angle or delay angle. So by controlling both, by controlling the alpha, you can control the output voltage. So you can increase or reduce the speed by means of controlling the VT, the armature voltage or the terminal voltage. Okay, so we look into single phase, and then we now it relates on the quadrant operations. Okay, so the quadrant operation, if we operate only half of the if you operate on the basic circuit, you can actually control, you are only in, yeah, where is that? Actually for this circuit, okay, you only work at the quadrant 1 and quadrant 2. I found something is missing here. Tak apa, nanti saya update that. Okay, so if you talk about the single phase full wave, a normal circuit there, which is okay, it's a normal circuit. So okay, the normal circuits there. Right. So we talk about the normal circuit, the normal full wave rectifier. You only work on quadrant 1 and quadrant 4 only, whereby you have omega and top there, or you can also take that as a voltage against current. Okay, so if you have only one, if you have only a normal full wave rectifier, you can only work for quadrant 1 and quadrant 4. Okay, so how can we make it as a 4-quadrant operation? How to operate that under all quadrants? We use the dual converter, right? So we have these dual converters. You combine two converters, and therefore you can work on all quadrants here. Quadrant 1, quadrant 2, 3, quadrant 4. Okay, and the equations. So this is equation again. So all of these are steady state equation, and we touch on the three phase, right? So this is a three-phase full wave converters, and we also touch on the chopper circuit, DC-DC converter, right? And it's a 2-quadrant, only work for quadrant 1. Then we have these circuits, and therefore you extend from quadrant 1 to quadrant 2. And finally, if you have this circuit, then you can operate your motor for all quadrants, quadrant 1, 2, 3, 4. Okay. Okay, so that is actually open loop system, right? Open loop system whereby if you want the motor to work at certain speed, you just change the alpha value, isn't it? you change the alpha, the firing angle, or you change the duty ratio of the DC motor of the DC-DC converter, isn't it? So you control the duty ratio of the DC-DC converter, and then you control the speed. So this is a open loop system. So how and normally in the complete system we don't do that. And we must have this closed loop operation so that everything is being done automatically. So if you apply a new, let's imagine you have a pump, for example, and you add extra load. When you put in more load, of course, the speed will reduce, isn't it? So in order for you to reduce the speed, to increase the speed, automatically you must sense. You must have a sensor to your speed, right? And then you feedback, and then probably you change that speed, convert that speed into a voltage. So there is a voltage ratio. I mean, the voltage constant. So then that voltage will be compared with the reference voltage, and then the error will drive the controller so that you increase the speed back to the required voltage that you want. With the additional of the load, but you still can maintain the speed via or through the closed loop system. Okay, so this is the purpose of discussing or learning this closed loop system. Okay, so this is a very basic concept from the control theory. Feedback is an important concept in circuit design. If I can. Okay, thank you. Feedback is an important concept in circuit design where a signal or voltage derived from the output is superimposed on the input. So you can see that now the output here can be feedback. Okay, so through that, you, for example, you have omega, we talked about omega already. So it is the sensor, so feedback that, and superimpose to the input. Then you compare with the reference voltage or reference speed, right? Reference speed, and that gives some error here. So that error will drive the we call it system here, and therefore you can increase or reduce the speed. Okay, so I hope you still remember this is again under control system, if I'm not mistaken, right? So you have GS, HS, and finally you have the CS equals to GS 1 plus GS HS, to get the transfer function of output. Let's say this is output divided by input. Great. So I hope you still remember that. So this call it negative feedback, positive, negative. Therefore, we have 1 plus 1 plus GS HS. Okay. So this is where you apply the control theory that you learned before into the real world, right? So you have this complete system there. Okay, so this output input path, so output input path can be used for several purposes. To control the output voltage, of course, this is our output voltage or anything, the speed, right? And then control the gain, reduce distortion, improve stability, create instability as in an oscillator. So this is some basic concept of feedback. A feedback control system consists of the building blocks shown in figure below. It includes the necessary elements, the signal path, so this is a signal path, right? A means of sampling the output. So this is the output sampling. You use a sensor, all right? Processing of the feedback signal. So you process the feedback signals here, and means of introducing the error signal at the input. So, and therefore you compare with the reference parameter here, and then that will create an error. So there is an error there, so that error will change whatever the transfer function that we have here, and therefore it will increase or reduce the output here. So this is the basic feedback system. In the simplest feedback system, the feedback signal processing may be one or two passive components with direct connection to the true circuit at the output and input. The feedback signal that is mentioned here is actually consists of the comparator, the discrete. Sorry. Okay. This is talk about the comparator, positive, negative. For example, then you have this resistor combined with a capacitor. Then you have another resistor here. Then that connect to the output. That connect to the input. Then you have a reference. Okay, so this is what is talking about the one or two passive components here. Yeah, so this is to represent the feedback signal processing circuit. The diagram can also become much more complex. Okay, so previous diagram here can be more complex, whereby you can have uh, another current controller here, for example, right? Somewhere here, then you have another, for example, somewhere there you have another GS here, G2 system. Then you want to come back to that. It can be complicated, cascaded, build, we call it a system, right? Can be complicated. But first, we only discussed the basic closed loop system for the DC motor. Okay, with extensive signal processing and the addition of reference signals, comparators, delay lines, and even multiple feedback loops. Okay, the speed of DC motor. So now we look into the speed of the DC motor, the closed loop control of the DC drive. So the speed of DC motors changes with the load torque, isn't it? Very clear, straightforward. If you add more load, of course, your speed will drop, isn't it? Right? So to maintain a constant speed, the armature or a field voltage should be varied continuously by varying the delay angle. This is the firing angle I mentioned just now, the alpha, or duty cycle. Sometimes we put it a D, but in the slide put it a K. So the duty cycle of DC-DC converters. So in practical, drive system is required to operate the drive at constant torque or constant power. So this is very practical. It's either constant torque or constant power, the load. In addition, control, acceleration, and deceleration are required. So you can also have the acceleration, pecutan, accelerate or decelerate, braking in practical. So we need to involve the closed loop feedback system. So most industrial drives operate as closed loop feedback system. I think I don't know whether we still have the manual. So I think most or all industrial drives operate as a closed loop feedback system. So there is no manual. If you talk about manual, you need some, probably your hands. You need some mechanism to change the manual mechanism to change the alpha and the system so that you can control the speed. So now we have a closed loop feedback system most of the motor drive. So advantages of closed loop system, we can improve accuracy, of course, by using that closed loop. You sense the output, and then you always have this error, isn't it? Because the speed sometimes can increase a bit, reduce a bit, small changes in this actual speed. So that will actually trigger the feedback system, and then there is a control error produced. So you have a constant improve of accuracy of the speed at any time because of that closed loop. And then fast dynamic response. What does it mean? When you give a step response, okay, so that's what does it mean is that when the load is suddenly increase, okay, because of that closed loop, you have a very fast dynamic response. So it will respond to that particular change in a very fast condition, right? Very very quick time, a few minutes, a few microseconds, for example, compared to the manual, isn't it? If you have a manual system, you have to measure and then you have to change manually everything, so that takes some time to respond to that particular change in the speed because of due to the load. But if you have a closed loop, it's very fast. Okay, they're automatically done, so you have a fast response and reduce effects of load disturbances and system non-linearities. And this is what we have: a load disturbance and system non-linearities could be from the system itself. There is an error, and so when there is an error, the system will respond to that and change the speed of the motor. Okay, so this is a basic the block diagram of a closed loop converter fed separately excited DC drive. I will recommend you. And now when I look into the slide and everything, I found out that we can use this Muhammad Rashid's book. So probably I can show you the book. Please, I hope everybody have a copy of this book, right? This is fourth edition, Power Electronics, Drive, Circuit and Applications. You could probably find the PDF file for that. And this is very recommended, right? So you have this DC drive, steady state operation, and also the closed loop operation. So please make sure that you found this, and we're going to use this a lot. Okay, right. The speed control responses with an increased control signal is changed. Did you see the book? I've just shown you the book actually. Nampak tak? Tak Tak apa, nanti dalam video nanti nampak. Because when I share the video recording session, you will see my face on the right hand side. Okay, so please go and look for the Rashid's book, Muhammad Rashid, Power Electronic Converter. Okay, so you can turn to page 73, discuss a lot on the closed loop operation. So we have this, right? So this is the armature that we talk about, right? It can be from AC converter, AC to DC rectifier. So that can be from DC rectifier. Sorry. Okay, that can be converter here, isn't it? So we have AC to DC. By the way, according to IEEE, if you want to write AC/DC, you have to have this small letter, and this is IEEE standard to write AC to DC. And it's not AC/DC. So this is recommended AC/DC. The small letter of AC/DC, you have a DC/DC. So it can be DC/DC, AC/DC, or DC/DC converter here that provide this VA, right? And then your DC motor, and then you have a load torque. This is a load torque. Then the speed, right? So there is a sensor here. So there must be a sensor somewhere here. Speed sensor. And give that speed back to the speed sensing. Oh, there you are. You have the speed sensing there. And then somehow here there is another actually that convert from speed to voltage, isn't it? There's actually another or probably actually involved in that. So this convert from speed to voltage, right? Some form of voltage. So that voltage we compare with the reference voltage. So this is a reference voltage with respect to the speed required. Okay, so what the speed that we need to work on, and then it compares that it turns into reference voltage, and from this side we have a actual speed and then convert into voltage, and both voltage will be compared, and that gives you the error. Then error will drive the speed controller, and that gives actually PC, and it either change the alpha, okay, or it can be duty ratio, D. Okay, right? So that will change the converter here, and therefore you increase or reduce the armature voltage. Right? So that is the complete the closed loop operation of the convert fed separately excited DC drive. So if the speed motor decreases due to the application of additional loop torque, the speed error increases. We jump to that particular. Increases. The speed controller responses with an increased control. So you increase that VC, change the delay angle, right? So you have delay angle alpha here, or duty cycle B of the converter, and increase the armature voltage. And increase armature voltage develops more torque. So more torque and increase motor torque to restore the motor speed to the original value. Okay? Based on PR here. Okay. So when there is no when speed, actual speed equals to reference speed, there will be no error. The error will become 0. But actually in the actual system, there must be a small error here. There must be a small error there, so that everything will operate. Okay, next. So now we look into the open loop transfer function. We have the steady state equation just now, right? Now we're going to look into the open loop transfer function. So here you need to have a lot, go back and look into the control system book. The one that I had is a nice book. This is from Norman Nice. I don't know which book that you use for your control subject, but for me, I have this actually during my degree. So I bought this during my degree, and it's, I mean, it's a good investment, right? So I still use it after what? After 20 years, I still use the same book, right? So from it's nice, you can refer back to your control system and look into the basic of the what is a transfer function, how to control into Laplace transform, Laplace transform and inverse Laplace transform. Okay? So that and again, and also find the Rashid's books. Okay, so a lot of derivation in the Rashid's book. So we're not going to go through all the derivation in the class. So I hope you can go back and then look into the derivation of the equation in the slides. Okay, so the steady state characteristic of DC drive are of major importance. Yes, it is important in the selection of DC drive, but they are not sufficient when the drive is in closed loop operation. So you cannot only depend on the steady state value. Okay, you must have another equation, which is known as a small signal model, a small signal model, and then that will determine the dynamic behavior, the dynamic behavior of your circuit, of your motor, and this is normally expressed in the form of transfer function. Transfer function T of S, Ts equals to Gs over 1 plus Gs, right? So they're always in the form of transfer function. And this is the basic convert the DC converter DC drive. We have this separately excited motor. So this is separately excited motor. Right? The field, the armature winding, the resistance of the armature winding, and we have also the inductance. In the field circuit is separately excited, so you have LF and RF, IF, EF. Okay, and we have this back EMF developed here. Okay, EB sometimes called EB. The speed of the motor, the torque developed by the motor, and it is always in the opposite direction to the EL. So we have a load torque against, it always opposite to the torque developed, and we have also B, which is the friction, right? We also have the friction, and actually we have also J here. I forgot to put J, the moment of inertia of the load there. And so we have this circuit, and then in the front end we have the converter. Okay, so it can be AC to DC, can be DC to DC converter here. And so this is the open loop. We call this as a open loop control. So the speed, the motor speed is adjusted by setting reference or control voltage. We are here. Okay. Assuming a linear power converter of gain K2, the armature voltage, the motor is K2 multiplied by VR. So it depends on the circuit, which circuit that you use. Okay. And we put it as a general gain. And we just put a general gain K2 here. The armature voltage. So you change the VR, you can change the speed, or you change the K2. Right? So there are two elements here. You change the K2, then you change the VA as well as the speed of the motor. So this is open loop operation. And this is the first equation. VA equals to K2 VR. And then we have a regular equation here. So you have EG equals to K VIF. So back EMF always start with K flux. So you always remember that K flux omega n 3. And then you can also, but we know that flux is proportional to IF. Right? So therefore, flux equals to K, whatever K1 if you like, IF, and therefore KV, here you have K, K1, IF, omega n, right? Therefore that KV equals to K multiplied by K1, so you just replace KV, IF, omega n. Right, so this is a basic equation. Then we have the KVL. So if you do the KVL, and you get this equation on the armature winding, right? So you have Rm multiplied by Ia plus Lm dia over dt, that equals to Eg, the back EMF, and you have this equation number 3. And then on the load side, you have the developed torque developed always again. This is similar to the general equation is always K flux Ia. And then same as we did just now, that can be replaced by KTIF IA. You can look at this notes here. KT is torque constant, KV is generator constant. And finally, you have this equation for the mechanical side. Sorry, this is mechanical side. We have J, the moment of inertia of the motor, multiplied by d omega over dt. Then we have P, which is the friction, multiplied by omega, plus the load torque itself, right? Equals to the developed torque. Okay, equals to developed torque. So this is a steady state equation again. This steady state. Okay, next. Transient behavior may be analyzed by changing the system equation into the Laplace transform. So you can change that into the Laplace transform. I hope you still remember. So how to change that? Do this steady. Okay, that did it. Then you have it. So that becomes Rm IAS plus Lm become SIAS plus EGS. Okay. So we have EAS. Okay. So that is a Laplace transform, or you can still remember that. And here you have DDS equals to JS omega S plus B omega S plus BS. Okay. So change that to Laplace transform, and that gives you this equation. 1, 2, 3 there. Then you can, from 7, you can get the equation for current. Just rearrange this equation. That gives you this equation there. Therefore, finally, you have VAS minus KVIF. So, and you can also change that the time constant. TA is always L MM. So that define the time constant, how long it will take for you to go into the steady state equation. So when we have a transient, you have a response transient, and then you have this steady state, isn't it? So that determines the time constant determines how long your system will get into the steady state equation. Okay. And from equation 8, the motor speed become omega s dt s minus. So you go back and look at that, and that also give the mechanical torque. Mechanical time constant. So just now we have a time constant, and this is the time constant for the mechanical side. So time constant equals to G over P there. Right. Next. And therefore equation, so you go back and look into the equation 6, 10, and 12 can be used to draw the open loop block diagram. So based on this previous equation just now, the 4, 3 equation there, so 3 equations there, so you can redraw and put into the block diagram from the equation just now. So you have omega there, then you have EL, EB, and this KV, then you have EG, IA, you can trace back, right? Start from there. So from the equation just now, 3 or 4 equation, so you build this open loop block diagram. So from that block diagram, it's easy for you to solve transfer function of the output against input, for example. So this output is so right. So again, you always have to have a clear objective. Why we do this? Because we want to control the speed in the automatic fashion. Or we call it as a closed loop operation. Okay, so you start with the open loop block diagram. Start with the open loop block diagram. Then we're going to add the controller circuit, PI controller, for example, PI control, then to complete the closed loop operation. Okay, so 2 possible disturbances are control voltage, which is VR. So to change VR, actually you can change the speed, and sorry, we call this as a disturbances. It's not a control. So if there is a disturbance in VR, as well as at the load torque here, the speed here will either increase or reduce, isn't it? So you have these 2 control speed. The steady state responses can be determined by combining the individual response due to VR. So you also can combine both equation, both, and then to get that can be the individual. Sorry, combining the individual response due to VR can be determined by combining the individual. Yes, of course, you combine both, everything, to get the steady state responses. Okay, next. Now we look into the response of the step change in the reference voltage. So you have a complete open loop diagram just now, and then you look into, you solve that, and you can focus on, look into what happens to the speed if you have a step change to the reference voltage. So you solve that equation, then you can get this transfer function. Okay, you get the long transfer function here. So if you plot in the block diagram, in the MATLAB, okay, you can actually see if you give a step change to VR, what happened to the speed? So for example, the speed is stable. At a certain point, you give you increase the VR, so it will increase to a certain level, isn't it? Yeah, omega 1 there, and then if you apply VR, so I'm going to draw again. So let's say you have a step change there. So this is your VR1, then you increase VR2. Isn't it? So you increase the value of VR from VR1 to VR2. That also actually increase the speed of the motor from omega 1 to omega 2. And this is related by this equation, the whole equation here. Solve according to the previous equation, transfer function equation. Okay, sorry, just understand the equation. Response due to a change in load torque TL can be obtained by setting VR to 0. So from that equation, sorry, you have that, isn't it? And you can also look into the step change due to the load torque. So now we're going to focus on what happens to the circuit, to the system, if you have an increase in the load torque. What happens to the speed? Yeah, the load torque. So you solve that, then you find out that this is your question. The Laplace transform, the transfer function with omega with respect to the change of EL. So you have this equation. Don't worry. Probably this is the first time you saw the equation. You found out the equation. Don't worry. You will get used with this equation, right? 1 over B STA plus 1 and the rest. Then finally, using the final value theorem, the steady state relationship of a change in speed delta omega due to a step change in control voltage VR and a step change in load can be found from equation 13 and 14 respectively by system. So you can actually find the change, right? The actual change by looking into the steady state. This is in terms of Laplace, isn't it? So if you want to have to know what is the change, then what you do is you set to 0 here, the final value theorem, and when you apply that, then you can see that this is the step change in load torque VR, the step change in the response voltage. What is it? This is control voltage VR, and then you can see the change or the step change of the delta omega. So now it comes down to this equation. By applying the final value theorem, you'll find the steady state relationship. So that gives you that equation. And for the load change, step change, you have this equation here. Okay, set the S equal to 0, then combine this equation. Okay, right. And finally, plot diagram for reference voltage and load torque distribution. step change in voltages now. We have this just now, the two block diagram of the open loop. The DC series motor are used safely traction, position. Oh, we stop at this particular block diagram because next is the series motor. Okay, so for this class, we only look into the basic, what is the closed loop operation. We look first on the DC motor with a separately excited configuration. And finally, we have this very important step change, open loop. Right? This is the open loop transfer function. And after this, we're going to look into the how you're going to add compensation, because based on this open loop, we're going to look at the dynamic behavior. The dynamic behavior of the whole system here. Then you can compensate, or you can put in the controller, PI controller, so that your speed becomes stable. You cannot rely on this open loop itself, or steady state open loop block diagram here, or transfer function to control speed. You must make sure that the speed is stable, and then to do that, we need the whole complete closed loop system. Okay, all right. That is very much our class today. Any question from the floor? Sorata. Okay. All right. Don't worry. So we have 22. Okay, great. So again, next week is our test one, right? Inshallah. We will, I don't know, probably simple question. I don't know. Because it's everybody have a different set of questions, which means each class, each lecturer have its own set of questions. Okay, you cannot compare with others. So I'm going to have my own set of questions. Let's have a look. Inshallah. Okay, thank you very much. Enjoy. So we're going to meet again on Friday, isn't it?
Yeah.
Okay, 8 o'clock, inshallah. 9 o'clock lah. Let me make it at 9 o'clock. Okay, if anything, I'm going to post on the WhatsApp. Test Rabu ke Jumaat. Rabu lah. Make it on Wednesday, boleh ya? Next week.
Berapa lah?
Apa dia tu?
Test tu. Jam ke? Jam.
During the class. 1.5 hours. Okay. So Rabu 8 o'clock. You start at 8 or 9 or 8:30 lah. 8:30 ke. Okay. Alright. Assalamualaikum warahmatullahi wabarakatuh. I'm going to share with you the notes afterwards, and also the recording session, video recording session. Okay. Assalamualaikum warahmatullahi wabarakatuh.
Thank you, sir.
Thank you. Okay.